Well, we're very, very pleased to have Balázs visiting. He is giving a lecture course at AIMS at the moment, and he's also come to visit us here. He's going to give a NITheCS colloquium talk on Monday next week, so look out for that. And then we've got this mini school that he's presenting on graded rings and projective geometry, both this afternoon and next week afternoon, which I think it's got a slightly later start next week, 3 o'clock. So Balázs is from the University of Vienna. I met him when I was doing a postdoc at Oxford, and he's a very, he just explains math very well. And so we just
you decide for yourself.
We thank you for being here. We look forward to it.
Thanks very much. Yeah, thanks for being here. Thanks for coming. So I think the background of people is mathematically you probably have different backgrounds. So I'll start very general, and then I'll try and make it more concrete in the second half of today's talk, and then I'll get a little more technical next week, but not too technical. But so my subject is algebraic geometry. I will be working with algebraic varieties. So I just want to give a very general definition and just of the main sort of setup, and then we'll make it very concrete. So the setup is that we have some ground field, so we're going to be working over some ground fields. Okay, it's going to be my ground field, and I will, if I need to, I will assume that it's algebraically closed of characteristic 0. So you may as well take in that case the field of complex numbers. I am working in complex algebraic geometry, and then so first of all, what is affine algebraic geometry? So affine algebraic geometry is the following setup. So I think that will be familiar to many people. So I'm going to decide what dimension I live in. So I'm going to be considering the ring, the affine space, say affine space AN. So this is simply n tuples of values, set of n tuples of values elements in the field. And then we are going to consider subsets of this that are defined as the vanishing of a bunch of polynomials. So the vanishing locus of some polynomials f1 of xi, fk, some number of polynomials. Or in a slightly more sophisticated language, so these are, so that the fi are simply polynomials in the variables that we have chosen. For now, we'll condition. And so we can say that some point is in x if all these polynomials vanish. And then one step up from this is we could say that or is the same as the vanishing locus of some ideal of the polynomial ring. So here I is the ideal generated by these polynomials. Okay, and that's an ideal of this fundamental ring of polynomials. Okay, x1 up to xn. So that's the sort of standard setup, and of course this goes back to high school mathematics, where maybe over the real numbers we could just take linear polynomials, and then we are talking about maybe the intersection of two lines in a plane, or the intersection of a line and the of planes in free space, and so on. So this is the sort of geometric setup. So this will always, in algebraic geometry, there is always a geometric setup. Now the algebraic setup is slightly different. So this is the algebra side. So we can consider a ring R, which is the quotient ring of the polynomial ring by this ideal I. And this is what's usually called, this is usually denoted K of x. This is what's called a coordinate ring of x. Okay, so this is sort of the geometric setup. Or we could start, so here we start from geometry, here we start from a space. So this is some space, and then this is some subspace. This is given by the vanishing of of some equations, vanishing of the Fi, some subspace. And then we create all this algebra. And we could start from the other side. So we could start in algebra. If we start in algebra, then I would say that I start with R, a finitely generated K algebra. So then this is going to be my data. And incidentally, when in this lecture, whenever I say ring, I mean finitely generated K algebra. So rings is the kind of word we use, but really my definition of a ring is just a shorthand for a finitely generated K algebra. This is going to be our. Of course, you can go more general, and you can talk about more general rings in this subject. But for me, every ring is going to be a finitely generated K algebra. And in fact, it's a technical condition. We don't need to know much about that. But I will want this to be a prime ideal to get some nice things. And correspondingly, I want this to be an integral domain. But these are not so important. Certainly not for this introduction. So in algebra, we start with a finitely generated K algebra. So finitely generated means that it has, I can fix a set of K algebra generators, R1 up to Rn in this algebra by assumption such exists. And then I can consider a ring homomorphism, so can consider ring homomorphism from a free polynomial algebra, x1 up to xn. So this is going to be S, a free polynomial algebra, to R, where I'm mapping the generators to Ri. So by definition, because these Ri's are an algebra, set of algebra generators, then phi is surjective. And then we can set I to be the kernel of this ring homomorphism, kernel of this K algebra homomorphism. And then we get, first of all, by the isomorphism theorem, that R is actually S modulo I, or isomorphic. And we can consider the vanishing locus of I inside the same affine space as I had before. So I can kind of go either from a bunch of polynomials defining a locus in the space. I can go to the algebra, create the ideal and the quotient, or I can go the other way. I can start with a finitely generated K algebra. I fix a bunch of generators, then get the ring homomorphism, surjective, and I recreate the geometric setup starting from the algebra. So this X, so X, which is this vanishing locus of I, this is what's called the spectrum of the ring R. So the spectrum has a more technical definition, but for our purposes, this is going to be good enough. So this really is at the heart of the algebra geometry dictionary. So we get this affine dictionary. So in the affine dictionary, I have X, which is the vanishing locus of some ideal. Then I can go to the ring, which is the polynomial ring modulo the ideal, or I can start with R, and then I can go to this surjection and X, which is the spec of R. So this will create me this spectrum. Okay, so this is starting. This is algebraic geometry 101. This is the beginning of course, various developments, and you can say a lot about, you can start talking about singular and non-singular varieties. Today I'm not really going in that direction. This is a starting point which I just wanted to recall, because this is kind of the context that we are working in. And one very specific example I want you to always keep in mind is the case of a principal ideal generated by one this is a very, very general and important example. And then the x is the vanishing locus of a single polynomial inside affine space. And this is what we call a hypersurface. Hypersurface in affine space A. And that's fine. And these are very important examples, and we'll see a lot of hypersurfaces on this course. So to be even more specific, I could take n equals 2, and then my polynomial f is just a polynomial in two variables, any polynomial, and then the vanishing locus of f is those pairs xy, such that f of xy is 0. That's inside affine space. And this is what's called an algebraic plane curve. So this is an algebraic plane curve. Affine. Okay, so if you've never seen this before, then this is probably a little fast, but do ask questions. Do interrupt me if something is not clear. I mean, this really is sort of the starting point of the whole course. So I can't, of course, fill in all the details, but this is the main thing to remember is just this dictionary between rings, finitely generated K algebras, and subvarieties of affine space. Yes, sure.
Is that phi very dependent on the choice of the
Okay, very good. So that's a good question. And up to, if you take a minimal set of generators, then up to isomorphism, that it will not actually depend. But yes, there is, I made some choice there. And it will be more important. Dependence is important, but here there is actually no dependence really on choices. Yes.
You haven't told us why do we want to go from geometry to algebra?
That is true. How many hours do you have? Right. So
You should
that's a fair
from
point.
algebra
I
to
mean,
geometry.
it goes both ways. These relationships go both ways. I mean, I would say polynomials is an incredibly general construction. I mean, as soon as you have algebraic operations, the thing you have is polynomials. The vanishing of polynomials is a very, very natural, very basic construction. This is the easiest way known to the Greeks in some form, and certainly known to Descartes and Newton in very similar form, to create interesting interesting geometric structures out of algebra. So of course you can soup this up. Why only using algebraic operations? Why only polynomials? But this is a very, very simple context that seems to arise in mathematics all the time. So that would be my justification, that a lot of questions can be translated into this language. Now, why the algebra geometry dictionary? That's incredibly powerful. I mean, you really have, on one side, you have the language of geometry, language of topology. I'm not going to explain in full the Zariski topology, but that's a very, very powerful topological language that you can use on the geometric side. And on the algebraic side, well, algebra is somewhere we have a lot of methods. We have a lot of tools. Decomposition of ideals, and you can local commutative algebra. I mean, I'm going to be using some of that in this course, but we have a lot of methods on the algebraic side, which all have geometric meaning, but which would not so easily be accessible on the geometric side. So this is a very, very powerful relationship between geometry and algebra. And I mean, where should I start? I mean, a lot of questions can already be translated into language of the conic sections. I mean, conic sections, conics and conic sections is already there. I mean, we already in high school we would treat that as a mixture of algebra and geometry. You want to work both on the polynomial side and probably on the geometric side. So my justification is that it's just proved to be a very, very fertile sort of technology to build things. I'll give some more specific examples just a little later. But I mean, it's a fair question, but both sides are somehow very powerful. You have a lot of tools on the geometric side, you have a lot of tools on the algebraic side. And of course, number theory would fit in. I mean, I'm not specifically talking about number theory, but on that general level, I could replace K with C, I could replace it by all sorts of other things. I could replace it with Q, I would get to Diophantine questions, I could replace it with finite field or its algebraic closure. Then you get into questions of mod P, arithmetic. I could replace it with QP. Then this is the mixed characteristic case. So this is mixing characteristic 0 and characteristic P. And algebra will not care, at least initially, the algebra will not care. I mean, everything I said in algebra and pure algebra, it doesn't matter what the base field is. Or indeed, you could be more ambitious and you could just work over a base ring, replace it with the ring of integers. Then you would be talking about some universal theory over the integers. And a lot of what I say will go through. And my choice of working over a characteristic zero ground field is just because I'm weak. I mean, you can be a stronger man and a stronger woman and work more generally over some more general base. You could choose as a base, you could choose some base ring, some base ring, I don't know, B. Your base could be some other K algebra. You could do everything over or some more general ring. So, you could go in many different directions and you would connect with a lot of interesting mathematics. I mean, Fermat's last theorem is of course the Diophantine equation, but it was proved by translating it into geometry. And it was all algebraic geometry. It was translating it into language of polynomial geometry. Yes.
So on the algebraic side, we start with an arbitrary finitely generated K algebra.
Yes.
Does this mean that every such algebra ring arises as the quotient of a?
By definition, I just proved it for you. It's finitely generated. So it's got a bunch of generators. You can surject, and you're done. Yes. By definition, a finitely generated K algebra is a quotient of a free. Sorry, when I mean algebra, commutative. Sorry, I should have said that. I don't even say it because commutative. Everything for me is commutative. That's again a choice, and I apologize I didn't say that. All my rings are commutative. Yes. There are non-commutative versions of this. That's a much harder theory somehow. That smooth, easy, straightforward theory is, yes, so all my rings are commutative. Unital commutative K algebra. But those are, by definition. And I've just, well, that's a short argument, yes. It's a bit surprising, that's right. Yeah. So, but it's true, yes. Quotients of polynomial rings is the same as just finitely generated functions. Right. So I don't want to do a lot of people sitting. I should probably just stay on these two boards, but that's fine.
No, you can go anywhere.
Go anywhere? No. Oh, I go that. So I don't want to stay at fine, I want to go projective. So what is projective geometry?
I think it's easy if you start on the other one. But you can do it either way.
I'm the speaker, you listen. So what is projective geometry?
On your match.
So what is projective geometry? And I'm going to go grade 1. There's going to be a grade 2. Grade 1. So it's always easier to start from the geometric side when one explains. So then we start with projective space, Pn. And what is projective space Pn? Again, over my base field, which I'm not going to put there always, but over my base field. And so there are really two ways to think about it. And one is a kind of more abstract definition, and the other one is more concrete. So the abstract definition is that it is a set of equivalence classes. So I take affine space one dimension higher, modulo the equivalence relation, which says that an affine vector is equivalent to lambda times an affine vector, where lambda is k star. So that's some kind of equivalence relation definition that all our students hate. So you can also say that this is a set of lines through the origin in am plus 1. So in this equivalence, some equivalence class of vectors corresponds to the line spanned by x. So that's the sort of formal definition. But then slightly more informally, it is affine space, and then together with a hyperplane at infinity. And again, because we haven't got many hours, I can't give full justifications to why this is considered. I mean, one of the easiest justifications to say is that this has much better closure properties. So this is compact. Because of this equivalence relation, this is, for example, if I consider over complex numbers, this is actually a compact topological space. And in some kind of classical topology, and so many phenomenal algebraic geometry, you really only see if you go to this compact space, that you can compactify your situation. And these sort of points at infinity are naturally added to our situation. And then because of compactness is so much better, that so much better behaved, that you get a sort of better theory working over projective geometry. So what is then, okay, so that's the space I'm working on. So instead of Fi space, we will be working in projective space. And then you want to define subvarieties of that projective space. So X is going to be, this is a very similar definition, vanishing locus of F1 up to Fk inside Pn. But now we have to remember that that these are not really points. Points of Pn are not really like n+1 tuples, but they're n+1 tuples up to an equivalence relation. So here Fi are going to be polynomials in n+1 variables, x0 up to xn. But we want to insist that they are homogeneous of some degree di, meaning that if I compute Fi of lambda x, then I'm going to get lambda to the di times Fi of x. So the vanishing of these polynomials is a well-defined subset. So Fi of x equals 0 is a well-defined condition. Okay, so this is the basic trick in projective algebraic geometry. So here lambda is a non-zero constant. So I can say that Fi of the equivalence class of x equals 0 makes sense because of this. So this means that this is a sensible condition. So another way to say is that you want the f function Fi to descend to the quotient, and that requires that it should be homogeneous. Sorry, it doesn't descend as a function, but its vanishing locus is well defined. Sorry, it's still not. Yeah. The vanishing locus is well defined. That's what I wanted to say. Okay, so once again, an example of this is projective plane curves. So the vanishing locus of some polynomial f of x0, x1, x2 equals 0 inside the projective plane P2, and these are projective plane curves. And there'll be examples very soon. Okay, so we've done this part. And I haven't written down the last thing, but the last thing is not so hard to write down. This is the vanishing locus, once again, of an ideal. So here the ideal is the ideal generated by the Fi, and it's supposed to be a homogeneous ideal. I put a little h here of the ring K x0, etc. So this little h just means it's a homogeneous ideal, meaning it's generated by homogeneous ideal. That just means that it has exactly such a set of generators. Okay, so that's this part, okay? And then we can still write down this last thing, which is the ring. I'll do it there. So finally, we get K algebra R, which is our polynomial algebra x0 up to xn over the ideal I. But this has extra structure because this is a homogeneous ideal. So this is a graded algebra. So what does that mean? So graded algebra, that means that R, the direct sum of Rn n greater or equal to 0, where R0 is just isomorphic to the base field, the constants, and then the Ri is generated by homogeneous polynomials of the xi, total degree, I'm sure before Rn, of total degree n modulo the ideal I. And because I itself is homogeneous, then this grading makes sense. So I'm taking things up to elements of some fixed degree. So when I take this quotient, that's still a grading. And graded ring means, so the main property is that if I take Rn times Rm, that's going to be contained in Rn plus m. So the grading is compatible with the multiplication. So this is the extra structure we get if we don't start in affine geometry, but we start in projective geometry. So we get a graded ring. And just to be very specific, if I have, let's be even more specific, if I have the vanishing locus of x0 squared plus x1 squared plus x2 squared inside projective plane P2, so this is my x, and then this R is the polynomial ring x0, x1, x2, modulo this principal ideal. And this is a graded algebra of where the generators have all degree 1. So these all live in degree 1, and then polynomials of some higher degree, and then modulo multiples of that quadratic polynomial that gives you the grading. Okay, so this is the key. I'll write down the definition one more time. This is almost our key concept. Certainly graded algebra is going to be very important. And then an important remark is that R is more or less by definition generated by R1 as K algebra. Okay, so it's degree 1 piece. So R0 is just a constant. That's boring. But R1, the degree 1 piece, has the x0, the x1, and the x2, and by definition, those are algebra generated. Okay, so now can we go back? Yes, of course, can go back. This is still okay on that side. Maybe I won't use the whole board, but I use half of it. So going back, so once again, we have gone from geometry to algebra. Now, from algebra to geometry. What is our starting point? So R is a finitely generated, graded, and then let's put it connective K algebra. So what does that mean? So R is direct sum n greater or equal to 0, so Rn. We have R0 is isomorphic to the base field. This is the connective part. Let me not explain that, but that's a sensible condition to put on a ring. And then we have the grading condition, Rn times Rm contained in Rm plus m. And we want this assumption that for now, R1 generates R as K algebra. So we can actually generate from degree 1 elements. Okay, so that's our starting point. And we can go back. Now I can literally just copy everything. So I'm not going to go through all the steps, but that means that R is isomorphic to K x0, xn, modulo some ideal, modulo the kernel of some natural homomorphism, once again, under a choice of generators. And then we can generate X, which is the vanishing locus of I, inside Pn, and we call this proj. The projective variety corresponding to this graded ring. So any questions about this? So I've gone back and forth from algebra to geometry, geometry to algebra in two different contexts. One context is the affine context, where I have affine space and just arbitrary polynomials, and the other one is the projective context, where I compactified my affine space to projective space, because that will turn out to be extremely natural and useful in many, many contexts, and then I have graded algebras of that type. Okay? Yes?
So, for this example at the end here,
Yes.
so could we write down explicitly the decomposition?
Yes. Yes. So R1 is actually just going to be generated by x0, x1, and x2. as a vector space, as a k-vector space, because this is quadratic. R2 is going to be generated by all the x0 squared, x2 squared, and then x0, x1, and then x1, x2. But now as a vector space, I have, well, that's a quadratic relation. So I have just one quadratic relation. Okay, and then what is R3? It's all the cubics modulo multiples of this one thing. Okay. Maybe I should say specifically for this thing S, I called it S before, and I'm going to continue to call it S. So S itself, so S is k of x0, xn. I'm going to give, for now, I'm going to give each of these variables grades 1. Is itself, this is a graded K algebra, where Sn is just literally the K vector space of all monomials of spanned by x0 to the a0, xn to the an, such that the sum of the ai is equal to m. Okay, so this itself is the polynomial algebra itself is graded by this convention. Okay, yes.
Is that I always homogeneous?
For projective ones, yes, by construction, because my generators are homogeneous, and then yes, so there's a little lemma that yes, the relation ideal of among a set of homogeneous generators is a homogeneous ideal. Yes, the answer is yes, and it's not difficult to show. It doesn't follow immediately from what I said, but it's a one line.
It comes from taking generators, which are.
It comes to yes. Yes. So, but again, if a graded algebra is finitely generated, then it takes a bunch of generators, and then it has a homogeneous generating set, because you can just take the generators and break them up into the homogeneous parts. So I didn't say that, but yes, I will always take homogeneous generators, but that's not a restriction, because if it's finitely generated, then it's finitely generated by homogeneous elements, because any element breaks up as a finite sum. So that's not a restriction. Okay, so this is almost a like good match, good sort of story, but it's not quite. So there is one thing here that if you kind of come from the point of view of like starting from affine and then move to projective, one thing that is very unnatural. And in fact, if you just insist on this setup, then you really lose a lot of interesting information, or at least lose a lot of methods. So what is unnatural here is this condition. Why on earth should we insist that we have a graded ring generated by degree 1 elements? So let's see what happens. So this is kind of projective geometry, grade 2. Projective story. I said that was a grade 1. Grade 1 started there. Now we are promoting ourselves to grade 2. So what is a projective story grade 2? And really to motivate it, I have to start from the algebra side. So let's think again. What is the natural thing to do? We say we want something graded. So I have R is a finitely generated, graded, connective K algebra. So you could still argue about connective. And of course, there are more examples and more interesting stuff if it's not connective, but I want to keep that. So once again, R decomposes into a direct sum, Rm, m greater or equal to 0. Again, it's a choice that I take it positively graded or negatively graded, but that's going to be general enough. I want this grade 0 piece to be just K. I want it to be a graded algebra, so Rm times Rn is contained in R m plus m. Okay, I want to keep all that. But I don't want to assume that my generators are in degree 1. I want to assume that it's finitely generated. That's the natural assumption to make. So as I said, because it's finitely generated, it is going to be generated by, so R can be generated by a finite number of homogeneous elements. So homogeneous elements just means that my generators AI live in some specific piece of my grade. Okay, if that follows, because I have a finite number of generators, I can break them up into the homogeneous pieces, and look, they still give me a set of generators. Okay, so that's fine. But what do I do next? I wanted to create that homomorphism. So now I'm going to get phi from some free polynomial algebra. Let's say, so AI, so 0 less or equal to I less or equal to n generators. So I get a map from a free polynomial algebra to R. I map xi to ai as before. But I want this to be a graded homomorphism. And this will only be a graded homomorphism if this gives, so I will have to give this graded algebra. So this is the graded algebra with the degree of xi to be wi, some weights. And so these wi are some natural numbers, major equal to 1, so 1, 2, 3, 4, and so on, because I said that I'm connective, so there is no, as a K algebra, there is just a constant in R0, but in some higher degrees, I have my generators, and they have weights. And so to make this, I want to make this into a graded K algebra homomorphism, and then I have no choice but to give these guys some grading. Now that's absolutely fine. I get a new graded algebra of this free polynomial algebra with a new grading. And so that's a natural thing to do. And then, indeed, R becomes isomorphic. So this is going to be my general S. And then R becomes isomorphic to S modulo the kernel of phi. And this is indeed, it's very easy to show that this is indeed a homogeneous ideal for the new grading. Okay, so something new happened here, and this really gives a lot of richness to the subject. It seems like a sort of pretty innocuous thing to do, but in fact, it gives a lot of flexibility, a lot of richness, because what we are naturally forced to consider in this grade 2 is just to abandon our kind of assumption that everything should be in degree 1. Everything should have its own degree, natural degree. Some, for this story, natural positive integer degrees. So algebraically, not much change, but of course, we have to think about what this all means. So let me just give a specific example like the one we did before. So let's see a polynomial ring in 3 variables. This will actually come back later, so it's nice that we already start discussing it now. Let's say we have, so example, what is this ring S if I have K, and I'm going to call them, if they have different degrees, I'm going to call them X, Y, and Z, and suppose they have degrees 1, 2, and 3. So what does that mean? Well, it's a graded algebra. It's S0 is isomorphic to K. S1 is isomorphic to K span X. X is the only degree 1 element. S2 is isomorphic to K span X squared and Y, because these are the degree 2 elements. S3 is isomorphic to K. Now I see Z, I see XY, I see Y cubed, X cubed, and so on. Okay? So SD is generated by X to the A, Y to the B, Z to the C, such that A plus 2B plus 3C is equal to D. So we are getting to get some very natural combinatorial problems here, which we are going to solve in some sense very soon. So it's a new type of ring. I mean, there's nothing wrong with it. It's a perfectly sensible mathematical construction. But suddenly something new happened. And once you translate it into geometry, then something even funkier happens. So how to translate this into geometry? So we have the algebra now. Okay, I'll repeat this. But we have the algebra under some sort of control. And indeed, this is going to be our general setup. So our general, this will be good enough for us. So general setup on the algebraic side is going to be our finitely generated graded connective K algebra, which I'm going to represent as a quotient of a free graded algebra where the degree of xi wi greater than 1 integer. This is some surjective homomorphism, and R is S modulo of some ideal. So this is going to be a general setup in the algebraic style, and this will provide a lot of interesting examples of really funky things. But now we seem to have lost the geometry a little bit, so let me bring back the geometry. So what's happening on the geometric side? Really, I sort of didn't say that, but this projective space, the interpretation of this projective space here, where would it be sensible to put that? So this guy is proj of S. So here S was still everything in degree 1. Xi, but the degrees are 1. So this is proj of R, and this is proj of S. So I want to create a similar thing. I would like to say that I want to consider the vanishing locus of the ideal I, but where does it vanish? Where does it make sense to ask for its vanishing? So this is then the construction. You have to live with something called a weighted projective space. And let me emphasize, so I learned weighted projective spaces in a very, if they throw the definition at you first, you don't really see where on earth it's coming from. But I was trying to present it in a way that makes it extremely natural, that if you really think about graded rings and how they're generated, it's just forced on you that you should consider weighted projective space. What is weighted projective space? So fix positive integers, W0, Wn. These are the weights. And now consider projective space Pn with these weights Wi to be the quotient of An plus 1, take away the origin, modulo an equivalence relation, which sets x0, xn to be equivalent to lambda to the W0, x0, lambda to the Wn, xn, or lambda non-zero. If you like that language, what we are really doing is we are taking a one-dimensional torus acting on this affine space, but we are taking it not with a trivial character 1, 1, 1, but with some non-trivial character. So that's really one way to think about it. And just for a moment, if anyone knows that language, it is sensible to think of it as some sort of GIT quotient of An plus 1 modulo C star or K star with this particular character of the torus. There is some kind of more sophisticated point of view on this, which I'm not going to explain. But on down to earth, this is what it is. So I should put a bracket here. So this is an equivalence relation. It's a perfectly natural generalization of what we had before, and it is some kind of space. So this is going to be our space. Now, it is itself a projective variety, so maybe I put this here as a comment. I won't use this very much, but in fact, you can put weighted projective space inside straight projective space. I might make some, so Pn of Wi actually lives inside some P big N as the vanishing locus of some ideal I Wi. So these themselves are projective varieties in the old sense. So they are projective varieties in the grade 1 sense. And then these axes that I'm considering are sub-varieties of that. Well, this turns out to be a very kind of silly way of writing them, because it's hard to explain at this stage, but writing things in weighted projective space is often a much more economical way of writing them. These embeddings are themselves very complicated, and actually under active study, what are the properties of these embeddings? For the purposes of my series, I really want to focus on this side, And I really want to focus on this setup of these general finally generated graded connective rings. So that is my setup. And what I'm going to do now is just give one or two basic definitions and then give some further examples of why this is a useful thing to study. But let me just make some general remarks here about why we're interested in all this. Maybe some motivation. So motivation for everything I say. So this kind of graded ring method, so constructing varieties in weighted projective space, is a nice explicit way to find new examples. And so one famous case of this was now about 30 years ago. So for example, what are called Calabi-Yau threefolds for string compactification. So these are not just interesting in mathematics, but the big excitement about Calabi-Yau threefolds started really when Candelas and collaborators some 30 years ago now realized or started constructing thousands of examples of Calabi-Yaus in weighted projective spaces. So before that, there was only a very small supply of interesting examples, and then this was extended to weighted projective spaces. Now, weighted projective spaces are examples of what are called toric varieties. I won't be talking about toric varieties very much, but you could replace it. Yes, you could say also toric varieties, more general toric varieties. The key feature of all these constructions is that there is something inherently combinatorial about the constructions. Of course, there are polynomials, but a lot of the stuff that one studies has a kind of very strong combinatorial feel to it, and so we have some methods beyond algebra. We also have the methods of combinatorics to study them. So that's So constructing interesting varieties. What are other motivations? So there are, I mentioned already that in particular there are Diophantine aspects. And we'll maybe see one or two other examples. Very naturally, some famous Diophantine equations are actually weighted homogeneous. So therefore, you can actually study them in this context and study their geometry naturally in weighted projective space. And there are connections to representation theory. A lot of these concrete algebras carry interesting representations. And they're often graded or even bigraded. So if anyone is interested in the theory of McDonald polynomials or the n factorial conjecture or parking functions of combinatorics of parking functions, and so on. Now, these are all fields where these ideas of graded and bigraded and not necessarily graded in degree 1 rings have made an appearance. So there are very concrete, and actually one of my recent projects is very much involved with that. And I knew more the algebra side. I had to learn the representation theory side, but it was very useful to be able to draw on the language of commutative algebra for our study. I'll probably not get there, but this is an important relation to go into. So there are connections to string theory, there are connections to Diophantine equations, there are connections to representation theory. So there are many correct connections. But what I would emphasize is that this is a very concrete subject. So one can do very concrete computations. I learned a lot of this from Miles Reid, and Miles Reid calls these sophisticated Sudoku puzzles. So if you like Sudoku puzzles, then you'll like this as well. Then what we are interested in is the structure of these ideals. So that's what I'm going to be spending most of my time in trying to understand, what is the structure of these homogeneous ideals? What can you learn from various measures. We'll have a very natural invariant of a graded ring in a minute, and we'll try and get structural results in commutative algebra and algebraic geometry using this language of graded rings and some related constructions. So that's kind of the motivation for why. If you are an algebraic geometer, many of you are not, but like when you, okay, so what sort of explicit varieties? I already mentioned Calabi threefolds, Fano varieties, K3 surfaces, but also other building blocks. So basically, if you want an explicit example for anything, then weighted projective space will give you, or some very natural variety of weighted projective space will give you some nice set of examples. So you can treat it as a toolbox for creating interesting examples, but it also does connect to lots of other interesting areas of mathematics. So that was my kind of sales pitch. Let's see. So
We could take a coffee break.
yes, yeah, as you want. Yeah, fine.
What do you think?
It's up to you. I mean, you're yeah. Let's take a 10-minute break or
Okay. Let's take a 10-minute
10-minute
break,
Yep.
and hopefully we might be able to get some coffee or tea in the tea room.
Okay. Yeah. So we'll good. Thank you. We'll start again in 10 minutes, and that's a good place to break. Yes.
Sessions, right?
Yeah.
Also
Yeah. So 20 past, and then I'll probably not go for a full other hour because we started late. So I'll do another 40 minutes.
It doesn't matter though, it's fine, you can carry on.
We could do a Russian seminar. People can just sort of. When the last person leaves. Okay.
Very risky.
Fine by me. You know, I'm not paid by the hour. Yeah, sure.
So, is it possible to which projective variety ones as the weighted projective variety?
Well, I would go the other way around. I mean, in a sense, I'll give you an answer. So we'll discuss it. We'll discuss it a little bit later. But I mean, naturally, every variety is weighted projective. Naturally, every embedded variety. I'll answer you later. I'll answer you later.
Starts with 0. Tuple starts with 0. It's 0 and the last one with n.
Yes.
Are we in for that?
Yes.
Roots of the polynomial.
Yeah.
Well, I mean, remember, roots of a polynomial are, we usually say a one variable polynomial has roots. I mean, here we have multivariable polynomials. Yes, I mean, in one variable case, this would just be the roots. So, I mean, one example of everything I said is that I could take n equals 1. I could take just a polynomial ring Cx. And then, actually, this is a principal ideal domain. So every ideal, if I have an ideal like this, is always generated by just a single polynomial. And then the vanishing locus of f is nothing but the roots, the set of roots. And the subset. Well, I mean, this is a very general discussion. I mean, what can I say? I mean, there are as many as the degree with somewhat with multiplicities, but like
Maybe.
well, I mean, first of all, I'm working over complex numbers, so the roots are complex numbers for me, so they don't just have signs. So, but you're right. I am telling you a very general story. My general story will not tell you anything about signs or anything. I mean, what you're asking is a very good question, which is a more specific question in terms of that's more. Yeah, so I will not say anything about that. For me, this is just a set of points with multiplicity. So this is just a set of points, alpha 1, alpha d, where there's some repetition. So it's like maybe some roots. And then maybe some more double roots. These are double roots or something. So that's all the structure I see. And that's all, these are all complex values. So I should probably draw them in a complex way. Now, then you can ask about, where are the roots or what? That's a very, I will not say anything about that. But yeah, it's a sensible question.
Do you know?
There must be hundreds of references, but I would have to look. I mean, I'm not a specialist in like science of roots. Subject people have been interested in it for a long time. So, but I can't give you a one-line answer. I don't know. But can look, but you can look. So I mean,
Yeah.
there are specialists. I mean, he doesn't come anymore. Alan Bearden used to come
Yeah,
a lot.
yeah, yeah.
So he would be one person to ask about complex roots of polynomials. He's a specialist in explicit complex analysis and complex geometry. I mean, start looking for literature, but I mean, there's nothing. Where did everybody actually go?
We're down.
We're down.
To the left.
Hello,
Hello.
coming to pick up my dongle.
I haven't the foggiest where it is. I'm sorry.
It's my 4,500. This is it. That's finished.
No, everyone has just sort of gone to take a coffee break.
Oh, okay.
Hello, by the way.
Hello, how are you?
I'm all right, and you? I think they'll be back any moment now.
Okay.
Uh,
Give me a few minutes to. I'm not sure if this is mine. I'm just gonna go check and bring it back. But this is the one that I'm collecting.
Okay.
Very heilig.
They're coming back for a part 2 of the same session in just a moment. Yeah,
Are they using this or is it just like that?
I'm not sure. Sorry.
Mine.
Il est occupé.
The motivation one,
Qui pourra mercredi. C'est notre jour. Pour l'instant.
Frank is a. Frank's at Masha Pavia.
Okay, so welcome back. I just realized during the tea break that I missed out one very important piece of motivation. I definitely wanted to say, in honor of Bruce in particular and anyone else. So one important motivation is topology, because one very important source of graded algebras is the cohomology ring of a variety, say with complex coefficients or rational coefficients. That's very naturally a graded algebra. Now, these are finite dimensional. Most of my algebras are not, but you can then talk about quantum cohomology, and that's not even finite dimensional. And in fact, studying the relationship between graded algebras and topology and graded algebras in algebraic geometry is a very fruitful area of study as well. So I should have included that as motivation. And from here, in a couple of quick steps, you can get to stuff like the Langlands program and geometric Langlands. I mean, you know, that is very interesting relations that incorporate study of cohomology rings as graded algebras. Okay, so that was just one thing I did. Okay, so back to square one. So where are we? We have our connective, commutative, graded K algebra, finitely generated. So our direct sum of Rn and greater to 0 and R0 is less than K. And then a very important invariant of this is the Hilbert series. So I have developed over many years this unfortunate habit of calling it the Hilbert series, but writing P for Poincaré. But it's the Hilbert series. This is the sum, it's a formal series, sum t to the d, and the k dimension of t. Sorry, I had n here, the same. That's the d. Okay, so it follows from the finitely generated assumption is that these are actually finite quantities. So this is a natural R series with positive, non-negative, positive integer coefficients. And so it turns out that that will be a big theme for us. So we want, so R is isomorphic to a 3 algebra modulo I, and to construct interesting examples and to study interesting examples, we will be very interested in the structure of this ideal I, and that will be in direct correspondence or direct correspondence. But from R you get the series, and you have the structure of the series. And there will be some kind of suggestions about what the structure of the ideal could be. So you will never, I mean, you're losing, of course, information. I mean, this is a very crude information about the ring or the graded ring. It's Hilbert series, but actually it carries a lot of information and will be able to spot some patterns, we'll be able to get some suggestions as to what the structure of the ideal R could be. And let me write down a very basic proposition, which is not difficult to show, but I will have a more precise form of this proposition later. But for now, this will be enough. So suppose R is generated by, as before, by graded generators A0 up to AN of weights W0 up to Wn as before, and then this PR of T is some numerator modulo product minus e to the Wi product over the number of variables. Is a little bit.
There you go. Sorry.
Okay. Yeah. Cool. And this is something I've colloquially called the Hilbert numerator. The Hilbert numerator in particular has a lot of information. So when I say structure of the series, I mean really it's Hilbert numerator. There'll be a lot of information that we can find out about the ideal just by looking at the corresponding Hilbert numerator. And just to be very specific, so proposition 1 or example 1 of this, let's take S to be just a plain polynomial ring with degree 1. All the weights are 1. Then the S of T is just 1 over 1 minus T to the n plus 1. So this is the simplest possible formula.
Let's do it. Let's do the calculation.
Let's do the calculation. I'll do example 1, baby example. First, S equals K x0, x1. Then S D is spanned by x0 to the D, x1 to the D, of dimension D plus 1. So,
okay, wait, hold on. Carlisle's not following. Those dots. Fill in a few more of the things in the dots.
To the D minus
x0 to the D minus 1 x1. Thank you.
Are you following now?
And the D plus 1.
Okay, just do S1 and S2 explicitly until Carlisle's following.
Squared.
Happy?
Okay. In fact, like this. Okay. x0, x1, x0 squared, x0, x1, x1 squared, x0 cube, x0 squared, x1.
Now, Flores will appreciate that.
This is S3, this is S2, this is S1, then here is S3 starting with x0 to the D, dot, 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 x0, x1. Okay? Right, so what is P S of T? It's some D plus 1, T to the D, D greater or equal to 0, 1 over 1 minus T squared over undergraduate analysis series. Okay. And then how about this one? So this here SD is homogeneous elements of K x0 to the D, with lots and lots of things of dimension, oh god, D plus n minus 1, choose D plus n, choose n, approximately that. I want n plus 1 integers summing to D, so I want, yeah, that's correct. And then if you sum that, then that's some negative binomial theorem that tells you that the sum of these is that. That's exactly the negative binomial theorem.
I'm sorry, and I know should be obvious that I did pull up the passage slightly. So yeah, like there's two of them. Yeah, there's three. Yeah, there's four.
Yes.
I fell off the bus when we got
T plus 1.
T plus 1.
T plus 1.
Yeah.
At 1, there are 2. At 2, there are 3. At 3, there are 4. And at D, there are D plus 1.
So I guess I fell off the bus. Just this is an obvious equals that I should have known, right?
It's the derivative of the geometric.
As a first year undergraduate in theory of series expansions, yes.
The derivative of the geometric series.
Yeah. Or the simplest example of the negative binomial theorem. Okay. Yes. I mean, this one here is precisely the negative binomial theorem. 1 minus e to the minus n plus 1 is that sum. That's the negative binomial theorem.
I think Professor Moriarty did his PhD thesis in that. If you
You don't do PhD thesis in quite this, okay? I mean, here we are summing basic series, okay? Right?
To what I'm saying.
And you can draw a similar picture. So, I mean, if we have,
Read your Sherlock Holmes again.
you know, it's getting harder and harder, but there is a three-dimensional picture, right? This is x0, x1, x2. There are the constants here. There is x0 squared. There is x0, x1, x1 squared, x1, x2, x2 squared, and you're literally slicing a cone, and then you get the binomial coefficients. D choose 2, the D plus 2 choose 2 there, and this layer is S0, this layer is S1, this layer is S2, and so on. And you have a whole layer. So this is your D plus 2 choose 2 for
now we can see the combinatorics starting to come.
yeah, and the whole thing in dimensions going up, but you're still slicing the cone. Okay, so that's the first example. Now the second example, which will give you a new proof of the first example, by the way. Example 2 is, what if I have a polynomial ring with freely generated polynomial ring, but the variables are W0 up to Wn, so our general case. Then PST is 1 over the product of 1 minus t to the Wi. So how do we prove this? So there we use some kind of analysis identity or negative binomial theorem, but this is even more combinatorial. So why? So maybe let's prove this. So proof. What is SD? So I wrote down SD before. SD is spanned by x0 to the a0, xn to the an, such that the sum ai wi is equal to d. Okay, that's the condition. Now, if I expand that, so on the other hand, it's 1 over 1 minus t to the w1, 1 minus t to the wn is equal to 1 plus t to the w0 plus t to the 2w0 plus 1 plus t to the w1 plus t to the 2w1 plus times all these terms. Now, if you multiply them out, you literally get all solutions to this equation. That's the real proof. And that actually proves that one as well without any analysis and nonsense and binomial coefficients.
Like for the generating functions for the partitions.
Generating, yeah, exactly the same way as generating function for partition. Exactly. So now, observe. Now, here, that this is equal to PS. Okay. So that's another proof, and that's maybe it's a different proof. I mean, that proof taught us something, and this proof also teaches us something. Okay, so we are on a roll. Next is the next example. So from where do I want to start this example? Let's do it like that. So let's take S to be a general ring, so weights W0, Wn, and let F be a homogeneous element in some degree D. So just one of these guys, some span of monomials, and let's take I to be the ideal generated by F. And let's take R to be S mod I. So this is the hypersurface case. So we have a weighted hypersurface. X equals proj. R is the vanishing locus of F inside the weighted projective space. That's the geometry. And what's the Hilbert function? So the Hilbert function is Ps of t is 1 minus t to the d over the product 1 minus t to the d. I goes from 0 to. Okay, so why is that? This is also not hard. So proof. What is this? What is this ring? So I have multiplication by f. So this is actually an example that we will generalize maybe a little bit. Sometime later. This is an exact sequence of S modules even. So it's an exact sequence of S modules. And if I really want to be honest here, then if I want this, then I shift the grading here. So now, so this is this means shift grading. Because this is a multiplication by an element of degree d. So if I really want to make it into an exact sequence of graded S modules, then I have to put in that grading. And we can, on degree d, it's additive. So you can just repackage from here. It easily follows. So Rd is Sd modulo a copy of Sd, sorry, Rm is Sm modulo Sm minus. As vector spaces. And if you think about that, you take dimensions, take the difference, and put in that shift, you get exactly this.
Do you do the simplest concrete example of that?
Yes. And I'm not sure it's going to look very different, but so what's the simplest concrete example? I mean, I'm not sure this will illuminate because.
But even, I mean, it will even.
Yeah, let's do it.
Take n equal to 2. You know, and I don't want to see any dots. I don't want to see any dots.
You don't want to see that.
I just want to make sure everyone's following you. Okay.
Okay, quadric in B2. Yes, so we have R is x0, x1, x2 modulo x0 squared plus x1 squared plus x2 squared. And so
and our task is to determine the dimension.
To determine the graded dimensions, and so R0 is k, R1 is k, x0, x1, and x2. Then R2 is k, x0 squared, dot. Modulo x0 squared plus x1 squared now as vector space. So this is now a vector space over k. So this is one-dimensional, this is three-dimensional, and this is 6 minus one-dimensional. Because we get the multiples of the constants multiplied by that. Are you happy, Carla? Stop picking on people.
Okay.
R3 is k, the cubics, modulo, again, whatever can be generated by x0 squared plus x2 squared, or then times x0 and x1, because they are both there. So the dimension here is whatever the dimension would have been there, 10 minus 3. And so if I make a series, then I'm going to have some e to the d. It starts, be careful, so 1 plus 3t plus some d greater or equal to 2 And then I have D plus 2 choose 2. Yeah. I get this wrong. Minus D choose 2 D. So D equals 3. I should have, 5 choose 2. Yeah, that's 10. And that's 3 choose 2. Bingo. Perfect. So that's the answer. Okay. And then that's equal to, I can take the two things apart. And so it's going to be whatever it was, going to be 1 minus t squared times whatever I had before, which is just this 1 plus vt plus 10t squared plus 15t cubed. So this is 1 minus t squared divided by 1 minus t. Thank you. Okay. So these are examples of this. And now I want to do something a little different. It will come to the same thing. But so the nature of this subject is we keep jumping between geometry and algebra. So now we have done a little bit of algebra. I now want to jump over to geometry. So what are we going to do? Start with some geometric information and try and get to some algebra. So how shall we do this? In what? Great. So okay. So next sort of starting point. And towards the end of the lecture, we'll understand where that starting point comes. Suppose someone hands you the following information. Suppose we have finally generated, commutative, graded, connective R with an oracle telling us that the dimension of RD is, well, 1 if d is equal to 0, that we assume it's connective, but it's d if d is greater or equal to 1. So what is this mystery animal? So what can we say about this ring? What can we do? What can we say? So no one tells us where the generators are. This is all the information we have. So this is like beginning to head towards a kind of Sudoku puzzle. Here is an animal. Some oracle told us these numbers. What is it? So what can we say? So let's try and build it up slowly. So I have R0. That's always a constant. I have R1. And okay, so the oracle told us that this is one-dimensional. So it has to be spanned by some generator. I call it X. Okay? So this is one-dimensional. This is also one-dimensional. What about R2? So our oracle told us that that's a two-dimensional thing. We already have one resident there. We already have X squared. So we have to have a new generator. I call it Y. So here X in R, X in R1, is necessarily a generator because we haven't seen it before. And here Y in R2 is a generator, is a new generator. And I mean, there is some indeterminacy here. I mean, to your question, this is not actually well-defined. It's only well-defined up to a multiple of X. So this was well-defined up to scale because it's just the basis of a one-dimensional vector space. Here I have a two-dimensional vector space. I know one vector. I have to choose a transversal to it, like some other vector. So this is not completely well-defined, but it's going to be well-defined up to automorphisms. So that's okay. Okay. So now what is R3? Well, in R3, we already know two elements. You may recognize this very soon. We know two elements. We have X cubed and we have XY. And now, okay, we were not told anything more by the oracle, but let's assume that we are in some kind of generic situation, and let's assume that they are linearly independent. We don't know whether it's the right assumption or not, because we don't have enough information at this point, but it's like a genericity assumption. If we are assuming that, then we must have one new generator. So this is in degree. This is the piece of the ring. This is its dimension over k, and this is who they are. So we have yet another ring generator. Another generator. Okay. What about R4? So in R4, you can see, okay, so who do we know there? We know x to the 4, we know x squared y, we know y squared, and we know zx. And we are expecting a dimension 4 thing. Once again, if we are in some kind of lucky generic situation, and these are linearly independent, which they will actually be in the story, then we are actually done. We don't need new generators. How about R5? And in R5, again, we will be lucky. X to the 5, x cubed y, xy squared, y z, that's degree 5, and also z x squared. These are degree 5, and again, seem to be lucky. We have exactly the right number that we want. And we are almost done. What about R6? So in R6, we are expecting a 6-dimensional vector space. Well, now you count the same thing. I'm doing exactly the same kind of combinatorics again, by the way, just with shifted weights. I have x to the 6, x to the 4y, xy squared, y cubed, z x cubed, z squared, and xyz. 1, 2, 3, 4, 5, 6, 7. So that's too many. So what happens here is there must be a relation. This must be modulo some polynomial f x y z. This must be a degree 6 polynomial, weighted degree 6 polynomial. Okay, so that's what you can do naively. This is when Bruce asked me to write everything out in great detail. Or we can do something else. We can just write down the series. What does the series tell us? Okay, 1 plus some e to the d. Now this looks like a d greater or equal to 1. Now, so there is a shift, right? So there is a funny shift happening here. And I did the calculation, and the homework for Bruce is to do this calculation. The answer you can write in 2 different ways. You can either write it like this, 1 plus t cubed over 1 minus t squared. And honest to God, I have done this calculation. That is the answer. It is an elementary calculation. Or another way to write this, which is the one we are going to prefer now, is 1 minus t to the 6 over 1 minus t squared, 1 minus t cubed. And bingo, somehow you recognize everything. We have our 3 generators, degree 1, degree 2, degree 3. Magically, they are here, here, and here. And we have our single relation in degree 6. So what this says, and indeed this is true, that if you take a generic, if you take the right ring, so if you take a polynomial ring in 3 generators of degree 1 to 3 and quotient that by degree 6 relation, you get exactly this. You get exactly this Hilbert function. So this oracle, what the oracle told us, the oracle was secretly telling us exactly this ring. And Bruce can't even close his mouth.
I've missed something here because
I haven't missed anything. There's a bit of a miracle happening.
okay.
Okay. We haven't missed anything. The oracle told us that we have this graded connective ring with these dimensions. That's all we know.
The proposition at the top told us that the Hilbert polynomial, or the Hilbert, was always going to take a certain form.
Yes, but now I'm saying that it's taking an extremely special
But
form.
we never had a theorem that said it was going to look exactly like this. Eh?
I mean, generally it won't.
Yeah.
I mean, our oracle, this is a very, very specific situation that we are in,
Okay.
where the oracle told us something.
So we knew what the bottom was going to look like, but we had no promise what the top was going to look like.
Well, I mean, this is a slightly, I mean, you know, at this stage, you have no idea what's going to, what anything is. So I will have to tell you, so this is the oracle. There will be an oracle.
I see.
Where does the oracle come from? I'll tell by today's lecture, I think I will be able to tell you what.
So if R was generated by this, then it would have this series. That's
all I know is if R had these graded dimensions,
yeah.
and some genericity assumption, then it would have to have.
No, but what I'm saying is that because R having those dimensions is very little information. I could say,
yeah,
if it had these generators, then I could use the proposition.
That's right.
Yeah.
Right. So
Yeah,
that's
yeah,
right. So
okay.
you would go right.
Yeah, okay.
So yes. So if I take, you're right. If I take kx, y, z degrees 1, 2, 3 divided by f6, then that gives me this Hilbert function. That's a proposition.
Yeah.
And if I unpack that function, I get to these dimensions. But what I'm saying is, here I got them backwards. And there is an oracle, which is geometry. And so this is a geometric oracle that we're going to use. Geometric oracle tells me these numbers. I go through the geometric oracle. Sorry, I go through the process. I mean, this was really just an illustration. What we are really heading for is this information. But then you want to check that what you get is compatible. But it is compatible. I mean, in general, the numerator is going to be more complicated, and we have to kind of do much more work. This hypersurface case is always easy, and I pulled out the hypersurface case for you. How many more? Maybe I'll do one more oracle, and then I'll tell you where this comes from.
Can I ask a question?
No. Yes.
Is the series point of view telling you that there is a way to choose X, Y, and Z so that those things are linearly independent?
Well, no, the series will never tell you that. Let me, maybe that will be the example for next time, depending on how long. Let me do 2 more examples then, and the second example will actually address your point. The reason, I mean, I tell you, okay, so here is, okay, let me write down a more general proposition. Again, we'll make this stronger if we have time next time. Suppose f1 up to fk are general polynomials of degrees d1 up to dk. And I'll spell out next time what do I mean by general. There'll be a definition of general, but for now I'll just leave it at that. Of degrees d1 and dk, and I to be the ideal generated by f1 up to fk, and r s mod I. Then polynomial that the series for this ring has the following shape: 1 minus t to the di. I goes from 1 to k, modulo, sorry, where polynomials in k x0, xn with weights w0 to w. Standard setup, module divided by the product of 1 minus t to the w1. Let's put j's here, and then j goes from 0 to number variables. So that's the general formula. General here is something called regular sequence. We'll hopefully get to regular sequences next time. But just look at the structure of this. So here is the simplest possible example of that, the trivial example, which already shows you the problem. Suppose I take k to be, suppose I take k x0 up to xn, and f to be xn. So what do I get? So I get that. So what is this ring really? R is just actually isomorphic to k x0 xn minus 1, right? I've just quotiented out by the last variable. It's a stupid thing to do, but I get the identity 1 minus t to the, so this is, the degree of this is wn, so 1 minus t to the wn over product of 1 minus t to the wi. J goes from 0 to n is the same as 1 over product 1 minus t to the wj. J goes from 0 to n minus 1. So you can, and this happens actually not, this looks like a stupid thing to do, but this kind of thing actually happens. So you don't know. There may be a degree 2 variable and a degree 2 relation, which comes from the other variables. So if this linear independence assumption actually fails, and in this case it doesn't fail, but in more complicated examples it could fail, then there could be some kind of cancellation in the Hilbert function. So the Hilbert function will never even tell you the full set of generators, because it may be that you're missing a generator. And probably not today, but next time I will give you a geometric example, which is actually a well-known geometric example. Where this, it happens almost all the time. And it's to do with degenerations in algebraic geometry. So this is actually an important question.
I didn't understand what you're saying. Are you saying this is one of those cases where there's a relation?
Right? I can't tell. Really, this R doesn't need this last guy. So, I wrote R as S modulo xn, but I didn't really need that generator because, here it just cancels. So this is a kind of stupid thing to do. I really took an unnecessary generator. But there will be other cases where you will have to take a generator, and there will be a relation in that same degree, and you will not be able to see that on the Hilbert function, because you can cancel terms in the Hilbert function. The Hilbert function will have this product numerator, product denominator, but if some degree happens to be the same as some w, then they will just cancel out. So you don't actually see that on the level of the series. But geometrically, you might be hiding some information there. And it's precisely this genericity assumption. So the genericity assumption might hold for some set of parameters, but you might degenerate where it might fail. Now let me give you one more example and then explain the oracle and then maybe stop. So let's suppose that instead of those numbers, the oracle tells us. So it's a new example. It's a new R. Graded, blah, blah, blah. I won't write it down, but the oracle tells us that the dimension of RD is 1 if D is equal to 0, and 2D if D is greater or equal to 1. So I won't go through the calculation, but a very similar analysis will give you the following answer. So under linear independence assumptions, you don't need, first of all, from here you can just compute the polynomial, or the series PR of t, and the answer is going to be 1 minus t to the 4, 1 minus t squared, 1 minus t squared. And this is going to be compatible with a ring, which is under this genericity assumption, you get the ring K x0, x1, y. So this is weight 1, weight 1, weight 2, like here, modulo a quartic relation. And now let me tell you where the oracle comes from. So exactly the same analysis, and here you once again make these linearly independent assumptions, which once again actually here they will be true. So once again this came from the oracle. So finally, and I'm afraid this will use more algebraic geometry. So this oracle really comes from geometry. So our oracle, our information of these dimensions, really will come from geometry. So what is the oracle? Again, there are different starting points, but for example, and all these cases will be in this example, start with some algebraic curve C and some point P, or more generally what's called a divisor, or some sum of points. D equals sum MIPI, divisor on C. And then we get a graded ring. So then we get a graded ring, and algebraic geometry gives us the following. Algebraic geometry gives us this thing called L of n times P. So this is all rational functions on the algebraic curve, such that the divisor of f, irrational function, if you cancel and the poles, I get some non-negative divisor. Okay, so I'm afraid this is another 2 or 3 lectures of algebraic geometry. So this will not be, if you've never done a course on algebraic curves, then this will be difficult for you. These are what are called the Riemann-Roch spaces.
But they have done all complex analysis.
Yeah, complex analysis, exactly. So all I'm saying here is this is some meromorphic function. Well, it has to be meromorphic on the whole of C. So here I mean projective algebraic curve or compact Riemann surface, if you want. Take some compact Riemann surface, take a bunch of points, and look at meromorphic functions, so that if I take the divisor of that meromorphic function, so poles minus zeros, plus add n times my point, then I get a non-negative divisor. So in other words, cancel poles f by n times p. It at worst has n times p as poles. So that's the Riemann-Roch space. And the Riemann-Roch spaces form a graded ring. So the graded ring I'm talking about is the direct sum of these Riemann-Roch spaces for n greater or equal to n. And it's quite easy to see that this is a graded ring. If I take a function whose divisor is cancelled by n times p, and another function whose divisor is cancelled by m times p, then I multiply them together, then I get cancellation. So this really is a graded ring. And it will be finally generated, again, for some abstract reason in algebraic geometry, which is that positive divisors are ample. So the corresponding graded ring is finally generated. And then who is telling me the dimensions? The dimensions are coming from Riemann-Roch, from the Riemann-Roch formula plus vanishing. So there is quite a lot of algebraic geometry hiding in these oracles. So in specific situations, the dimension of this Riemann-Roch space is computable by Riemann-Roch plus vanishing. And now, if you don't know algebraic geometry, you just have to believe me that there is some kind of machine that produces such formulae. And where did these formulae come from? Our examples came from, and I should have called this, I call them R. This is a new R, let's call it R tilde. Where did this come from? So our examples, so the R came from C, a genus 1 curve, and then P is a point on the curve. And then you just write down Riemann-Roch for genus 1, and then you get that the dimension of L times L of NP is exactly n for n greater or equal to 1. And is 1 for n equals 0. So these are exactly coming from Riemann-Roch. The oracle was the Riemann-Roch theorem in algebraic geometry. And for this R tilde, I have the same C, genus 1, but I take the divisor, which is twice the point. So I can, instead of P, I can put some divisor D here, run through the same thing. So I'm going to taking the even functions with poles that can be cancelled by an even multiple of P. And then once again, Riemann-Roch will tell me that the dimension of L of n times D is 2n. And what were these things? What were these geometric models that we found? At least with this genericity assumption, which actually is going to be true here. So these x and y are z and z are literally just functions on the elliptic curve with a certain number of poles at some fixed point. So these are, complex analytic objects. I mean, they're basically the Weierstrass P function. I'm basically telling you the theory of the Weierstrass P function, but in this graded sense. So what was R? R corresponded to this model K, X, Y, Z, modulo F6. And this is actually the Weierstrass model of the elliptic curve, but in a twisted form. So what is this? So this is saying that my curve is actually isomorphic to a curve, which has, and the generic degree 6 equation, actually, you can bring in this form, z squared equals y cubed plus a y x to the 4 plus b x to the 6 inside weighted projective space with weights 1, 2, 3. So this is a homogeneous equation of degree 6. Just by eliminating some terms, just by some trivial transformations, you can actually bring the equation of every elliptic curve into this form. And that's what was the natural Weierstrass form. It really comes from considering your curve with its one point and taking multiples, and then you get this equation. So it's like the Weierstrass equation, but it's a little bit twisted, and it's a weighted Weierstrass equation. But it's very nice. This is degree 3, this is degree 2, and this is degree 1. So everything is okay. This is a degree 6 equation. And then what is the other thing? If R tilde gave us the following picture, so C is isomorphic to some equation y squared equals f4 x0 x1 in weighted projective space 1, 1, 2. And okay, there's a little bit of algebraic geometry that I want to close here. There's a map here to P1, a map here, and this is a double cover. So this is the model of an elliptic curve as a double cover of P1 branched over 4 points. So we recover from this purely algebraic construction and the oracle and the numbers, we recover some very, very natural kind of embeddings of our elliptic curve. And if you do this, I'm not going to do it, but you can do it with R triple tilde. So R triple tilde, the oracle would, sorry for the board technique, but double tilde, we have a 3 here, corresponding to 3 times a point. And then you actually just get the corresponding function is just 1 minus t cubed over 1 minus t cubed. And that really gives you C as isomorphic to a cubic curve in x0, x1, x2 inside P2. So at this point, you finally recover the standard embedding of the elliptic curve as a plane cubic.
The other way, it should be P1 or P2 that went in blue?
This is P1.
P1.
I'm losing, so this map is x0, x1, y to x0, x1. So I'm losing last. I mean, that's not a morphism here because it's not defined as 0, 0, 1, but it becomes a morphism here, and it's branched over the roots of this, exactly the roots of this polynomial. So it's a double cover branched over 4 points. And so you get in one fell swoop, you get the standard plane cubic, you get the double cover of P1, and then you get this funny Weierstrass equation in this weighted projective space. And they all come from the analysis of gradient rings. So I think I'll stop here, but yes, there'll be questions. But I think I'll just want to stop the talk here. This is a nice natural topic.
Just one thing. So I want to try to understand. Yeah. So yeah, you take a genus 1 curve and you compute the dimension and you observe that they have that.
Yes, I mean I'm just using Riemann-Roch. So what is Riemann-Roch? The dimension of L of n times p is 1 minus g plus the degree of n times p minus the h1, but that will vanish. That's it. So this is just the degree of n times p. This is just n.
So the next step is you move to the algebra.
Yes, so then I want to understand the ring. Yes.
You ask yourself, what are the rings which have this property?
What could be a ring which has this property? Yes. Can I manufacture rings with this property? And in this case, it's very easy. So if I feed that into the equation, if I feed from here, from these numbers to the series PR of t, it's a completely determined process. And I get this answer, right? There's no guesswork here. That's just feeding in the numbers. And I look at, I mean, if, I selected examples for you, but if I look at this, then it's obvious. I want a degree 6 hypersurface in this weighted projective space. There'll be more complicated examples. But these are the easy examples.
It will define families of curve which are labeled by that dimension of your graded ring.
Yeah, right. I mean, you're right. There is some compatibility here between the dimension. Yeah, right. I'm hiding a lot of these technicalities. If you just give yourself a bunch of random numbers, then you're going to get a pretty random looking Hilbert function. I mean, it may still be interesting, but I'll address these points a little bit. So I carefully selected examples for you, but yeah, let me do one final example, which will start showing you a little bit of the complications. So let's suppose that the oracle tells us this numbers. Dimension of RD is 1 plus 3n, 3d. I'll tell you where this comes from in a minute. Let's suppose that the oracle tells us that. Okay, so once again, it's a completely deterministic process. I go through the process and I get that the series looks as follows. Again, I did this calculation. It's 1 minus 3t squared plus 2t cubed modulo 1 minus t to the 4. Okay, so this is not as nice as anything that we have seen before. In particular, this cannot be factored. This is not of the form of my product of 1 minus t to the dn. Okay, so it doesn't fit into the one general pattern that we saw. So what is this? Where does it come from and what is it? This is in fact something we again know very well. This is actually the dimension of L of 3dp for C just P1. So genus 0. So genus 0 Riemann-Roch would say, that was my Riemann-Roch, it disappeared, but 1 minus g here, 1 minus g plus degree, the g is 0 now. So I get exactly those numbers. And what is this embedding? This is just a triple, it corresponds to the triple Veronese embedding of P1 into P3. So the ring I've taken is just a Veronese subring. So this really is just, so this situation here, the proj of R is just the image of the triple Veronese of P1 inside P3. Now that's not a complete, this is of course, we teach this in algebraic geometry. This is not a complete intersection variety. This is not cut out by 2 equations. And you see that it's cut out by 3 equations and 2 syzygies. So we'll come to the equations and syzygies in a minute. But so this is a determinantal variety. This is described by determinant by the rank of x0, x1, x1, x2, x2, x3. That's equal to 1. There's some equations here, but you start to see that this is a more complicated variety. This is not a complete intersection variety. Its Hilbert numerator is not in this product form, but we know that. The Veronese image is not a complete intersection. So this is the kind of thing you're beginning to see if you do more complicated examples. And in general, anything would happen, and we'll try and tame it a little bit next time.
So it's like that famous thing in Riemannian geometry, you have that saying, like, can you hear the shape of a drum?
Right.
And you're doing in algebraic geometry.
It's a version of that.
Can I hear the shape of my space from its
Right.
dimensions?
That's right. That's right. I mean, you will always get a moduli space of things, right? A cubic curve. Of course, I won't be able to tell which cubic curve. That's in the polynomial, but it's some kind of core classification. So that's when I say constructing varieties and their moduli would be more, and the moduli spaces. Because often if you can make a construction, then you can at least study maybe an irreducible component of the moduli space by varying the equations. So yes, I mean, of course, for P1, there is no moduli, it's just P1. But as soon as you have an elliptic curve, and of course, for the elliptic curve, we saw the moduli parameters. I'll probably delete them. But like the A, B, the A and the B are basically the combination of A and B is the moduli parameter. Like in the normal Weierstrass, sorry.
Yeah, thanks for us.